Okay, so this is part 2 of the AP Calculus AB Semester 2 Final Review. Number 1 here, find the volume of the solid obtained by rotating the region under the graph of the function about the x-axis over the given interval. So this curve right here in quadrant 1 would be the curve for 1 over x squared in the closed interval from 1 to 4. And we're going to rotate that about the x-axis to come up with the volume of this very cool solid right here. So how do we do that? Well, let's go general. Okay, volume is going to be my lower bound. When it's in terms of x, we're going to use an A, upper bound, B, and then you've got that function that you're about to rotate, and it creates what we call these area cross sections right here, which in this case, the cross sections are going to be perfect circles, and then don't forget your differential of x. That's your general volume formula in calculus right there. All right, so let's put this together. Okay, so again, circle. So we're going to have pi r squared, pi, and the radius of each of these circular cross sections is going to be output of the function. All right, so that's going to be f of x, but we have to square that, pi r squared, differential of x. Okay, so let's go our lower bound now, which our lower bound up there was a 1, our upper bound a 4, and if I take this f of x and I square it, I'm going to get 1 over x to the 4th, or x to the negative 4, and differential of x. And now let's do this. So that's going to be, what's the antiderivative of x to the negative 4? With the power rule, that'd be x to the negative 3 over negative 3. All right, and that would be from 1 to 4. Now I could bring that negative 3 out or leave it in. So either way, it looks like I'm going to bring it out. Could I go negative pi over 3? Yep. And then I have 4 to the negative 3 would be 4 times 4 times 4. What's that? 64, I think. And that would be my divisor. So I think I have 1 over 64. Yep. And then minus 1 to the negative 3 would be a 1. So let's clean this up a little bit. All right, so I've got pi, all right, and now think about this. This is 1 over 64 minus 64 over 64, which is going to be a negative 63 over 64. Okay, and let's clean it up. Negative times a negative is a negative. That's 11. So let's see, 11, what are you talking about? How many times is 3 going to 63? Would that be 21 times? So 21 over 64. There it is. Pretty cool, huh? Okay, sketch the region enclosed by the two curves and find the volume of the solid obtained by rotating the region about the x-axis. So same situation here, except now we're rotating not just the boundary of a curve, but a region. So this is going to create, instead of circular cross sections for the area, it's going to create washers or annulus. So x squared. All right, let's find some intersection points here. So can I go x squared equals 2x plus 3? Put this into quadratic form. So x squared minus 2x minus 3 equals 0. Let's hope that's factorable. So it looks like I'm skipping that part. Must be able to see it pretty clear. Yeah, would that be an x minus 3 and an x plus 1? So I'm seeing a negative 1 and a 3 right there. Now plug those into my y equals x squared or the linear. It doesn't matter. So negative 1 squared would be a 1, and 3 squared would be a 9, and there's my 2 points of intersection. Negative 1, 1, and 3, 9. Right there. Okay, and now we got a linear curve going through those 2 points, and we got the quadratic, and you know what the quadratic is going to look like because that's your parent function, so it's going to do this. There I have, kind of rough sketch, but it's going to work. Now, let me see. Did they give us an interval here? Sketch the region enclosed by the two curves about the x-axis. So my bounds are going to be the negative 1 and the 3 right there. So let's go general here again. So washer, that's right. So I'm going to have a pi, okay, a to b, and then my pi. And then it's going to be my upper curve squared minus my lower curve squared, and then my differential of x. All right, let's finish this, baby. So f of x, well, the upper curve is the line. So that's 2x plus 3, quantity squared. Oh, there's my balance too. And then my upper curve right there, my lower curve will be the quadratic, which is x squared squared. All right. And let's clean this up a little bit. Looks like we're going to do this whole one by hand maybe. All right. So how about we go 4x squared plus 12x plus 9 minus x to the fourth. And then I did it on the calculator, and I got 1,088 over 15. Don't forget that pi. 1,088 pi over 15. All right, next, sketch the region enclosed by the two curves and find the volume of the solid obtained by rotating the region about the x-axis. So same type of problem here again. All right, so let's not forget what secant and cosecant look like. 0 to pi over 2. Well, it's not a very big interval right there. All right, now isn't secant the reciprocal function for cosine? So it's going to do something like, oh, I don't know, this right here. And then the cosecant's going to do something, you know, like this right here. So secant, there it is right there. And now what's my cosecant going to look like? There you go right there. So let's see what we got here now. Sketch the region closed by the two curves and find the volume of the solid obtained by rotating. Okay, y equals secant, y equals cosecant, y equals 0. I don't know, that looks like 3 curves to me. And from 0 to pi over 2. So here's my region right here. And I'm going to make my life a little easier because this looks like 2 congruent sections. So I'm probably going to do half of it right there. Okay. So I'm going to go like this about the x-axis. So I'm going to go from A to B. And then area, differential of x. Okay, so here we go. Okay, so A to B, and these are going to be circular cross sections, and I'm going about y equals 0, and from here, so y equals 0, so I'm talking this right here. Okay, so pi, and we got f of x squared right there. Okay, so now let's just go, it looks like I'm going to have some stuff out here. Let's go from 0 to pi over 4. So I'm going to do half of that. And then I got to multiply this by 2. So how about a 2 and then a pi right there? And then f of x, that's going to be the secant. Oh, and I see where this is going. Secant squared of x dx. Right on. All right. And what is the antiderivative of secant squared? Isn't that tangent of x? From 0 to pi over 4. All right. And let's go tangent. Fundamental theorem of calculus. Tangent of pi over 4, that'd be a 1. And tangent of 0 would be a 0, and that's going to be 2 pi. Oh, how cool. All right. Find the inverse of f of x equals x minus 2 over x minus 1, and determine its domain and range. So the inverse must exist, so we could just interchange variables if we wanted to. Okay, looks like I'm going to start with the domain and range of this baby right here. Do you guys agree x cannot equal 1? And wouldn't I have a horizontal asymptote of 1? So y cannot equal 1 here. There we go, right there for the range. Okay, and there it is right there. Exactly. Do you see the vertical? X equals 1, vertical asymptote. Y equals 1, horizontal asymptote. Very cool. All right. So f inverse. Well, let's interchange the variables. So I'm going to call f of x x. And then I'm going to go y minus 2 over y minus 1. Okay. And let's solve for y. So I'm going to go xy minus x, or x times the quantity y minus 1. No, I want xy minus x, y minus 2. Let's get our y's on the same side. So I'm going to go xy minus y equals x minus 2. And then I'm going to factor out the y and divide right here. So I skipped a step, it looks like, you guys, but do you agree I have an x minus 2 up top? And then if I factor out the y, I'd have y times x minus 1, so that's x minus 1. And do you guys realize that this function is its own inverse? Well, that makes this rather easily. So the same domain and range. So the domain is still x cannot equal 1, y cannot equal 1. Even if you flip-flop, that's what you get. All right, and find the inverse. We got the inverse. We've got the domain and the range. We're done. Oh, look at that too. So I graphed f inverse, and do you see y equals x right there? Okay, this function has symmetry for the line y equals x. That's why it is its own inverse. Very cool. Okay. Oh, I love this stuff, and there's several ways to do this, but I'm sorry. When I look at this, natural log of e to the 3 isn't that 3? Natural log of e to the 4 isn't that 4? And 3 plus 4 is 7. Now, there's other ways you could do it. You could bring the 3 out front and all kinds of cool stuff. Looks like I'm doing it like this. I'm going to combine these. So isn't that going to be the natural log of e to the 3 times e to the 4? Let's see. Yep. And that's going to be the natural log of e to the 7. And you can bring the 7 out. 7 times the natural log of e is 7 that way. Okay? Or you can do it this way. What did I do here? Okay, I'm running out of ways. Oh, I went 3 natural log of e probably, 4 natural log of e, and of course natural log of e is 1, so that's 3 plus 4, and you still get 7. Lots of ways to do that. All right, loving this here. What is the antiderivative of 1 over x? Wouldn't that be natural log of the absolute value of x? But if you look at those bounds, you don't even need the absolute value here. And I think I got a little shortcut for you here too. All right, isn't that going to be the natural log of b over a? Yeah, so look at this. It's a 1 because that would be the natural log of e over 1, which is the natural log of e, which is just a 1. Bam. All right, hey, let's go back to pre-calculus here now, all right? We got to solve for the t. So I divide by 7. E to the 5t equals 100 over 7. Now let's do natural log of both sides. So that would be natural log of e to the 5t is 5t times natural log of 100 over 7. Okay, and that means my t equals the natural log of 100 over 7 divided by 5. All right, let's differentiate, okay? We got a rule for these too, don't we? The derivative with respect to x of the natural log of f of x is f prime of x over f of x. So boom, so I could go 3x squared over x cubed plus 1. This one right here. All right, prime equals, okay, well, the derivative of sine, root sine, so that'd be sine of x to the 1/2 power, so that's 1/2 sine of x to the negative 1/2. And then I got to go chain rule here times the derivative of sine, which is cosine. Okay, and that's over sine to the 1/2, or root sine of x right there. And oh, I can bring this on down. So that's going to be a 1. I got the cosine up there, 1 cosine. And if I bring a root sine of x down, I just get sine of x. There's my factor of 2 there, so that looks like a 1/2 cotangent of x. Right on. Number 11. Oh, logarithmic differentiation. These are fun. And yeah, Malcolm, we're not doing this the long way again. Okay, so here we go. All we're going to do is take the natural log of both sides, just like that. And now we use our laws of logarithms to rewrite the right-hand side. So that's going to be what? Okay, the natural log of x plus 1 quantity squared. And what did I do with the square? I brought it out front. Plus the natural log of 2x squared minus 3. There that is. And then minus the natural log of x squared plus 1 to the 1/2. And what did I do to that 1/2? I brought that out front. There it is right there. Now, again, the natural log of f of x. And this side right here, this is going to be easy. So what is the derivative of the natural log of f of x? Isn't that going to be f prime over f? Yep. There it is right here. And now let's do our derivatives over here. Okay, 2 comes out front. And isn't that going to be 1 over the absolute value x plus 1? Let's think about this a second. There you go. And why didn't I need the x plus 1? Oh, because my domain of the natural log stuff. Okay. And then right here, I've got a 1 over, okay, hang on. What did I do there? Okay, 4x. Oh, derivative of 2x squared. All right, over 2x squared minus 3. Okay, Good, I got it there. Got it there. Okay, and I'm just doing f prime over f on each of these is what I'm doing right here. So then I got my negative 1/2, and then I got my 2x over x squared plus 1. And now we're going to multiply both sides by f of x. So f prime of x equals, and what's f of x? So there it is up there. And now let's clean up each of these. So I see a 2 over x plus 1. I see a 4x over 2x squared minus 3. And then I see a 2's cancel right there and a minus. So I got x over x squared plus 1. There it is. Right on. Okay. The population of a city is P of t equals 2e to the 0.06 t in millions, where t is measured in years. Calculate the time it takes for the population to double, to triple, and to increase 7-fold. Now, you could work these all out, but if you understand what's going on with your natural logs, there's a shortcut to this too. Okay, so doubling time, okay? All you're going to do is natural log of 2 over the k right here, okay? Now, watch this. So, on these, if I want this to double, all right, I'm going to go to the natural log of 2 over, and isn't my k 0.06? There it is right there. You can leave it like that if you want. Okay, triple natural log of 3 over 0.06, and 7-fold natural log of 7 over 0.06. And you could do those as decimals too by actually solving each of them by hand, you know, which I'm not a big part of that, but you're going to get the same thing every time. Because here you would go what? The natural log of 2 over 0.06, then punch that out. 11.552 years. Go 7 right there, or we're 3 next. So natural log of 3 times 0.06, so that's going to be the natural log of 3 over 0.06. You punch that out and do the same thing on the last one. And there you go. You get it either way. All right, but if you remember this little shortcut right here, it's going to make you way more efficient. Okay, 16. Well, let's take a look here. I'm looking at the clock too. I'm going to run out of time. Hopefully I can finish this for you guys. Let's find out though. Okay, well, x is approaching infinity, so that's going to be 0 times, and that's going to be an x cubed infinity. And isn't 0 times infinity one of our indeterminates? So I think we can do a little L'Hopital stuff here, right? So I'm going to write it as a rational expression, so I can do that. So can I write this as the cubic over e to the x? And now I do my derivatives. Thank you, L'Hopital. By the way, this one right here, let's double check. And it's still, that's infinity over infinity. Still indeterminate. So let's go 3x squared minus 2x. And check this one out. And that's going to be infinity over infinity. So let's do it again. 6x minus 2 over e to the x. And that's still going to be infinity over infinity. So let's do it again. And you've got a 6 over e to the x. And that's going to be 6 over a number approaching infinity, which is going to give us a 0. All right, L'Hopital. So now number 20, differentiate. F of x equals 4 to the 3x. Now you remember these rules right here? The derivative of b to the x. The derivative with respect to x of b to the x is going to be, and you're going to have that natural log of b times b to the x. Simple. Okay? So let's set this up like this. I got a natural log of 4 times 4 to the 3x. And I think I got what chain rule going on there. There's a 3 right there. All right, and this one's going to be the natural log of 5 times 5 to the x squared, like that, and chain rule 2x out front. And there's those. Okay, and you might want to highlight this theorem too, because I'm probably going to give you this on a final. We'll find out. Okay, as well as make sure you know your laws of exponents and your laws of logarithms. And I think we're good to go here. Yeah. Okay, so that's part 2. Let me close this out, and I'll get this in Google Classroom, and we will go over all of these in class, and I promise I'll take a little more time.